Okay, so today it's the jet differential day, right? So I'll try to explain this construction, which is the first time you see it, it's rather involved. The second too, but yeah, but the third a little bit less. So, okay, so yesterday I was discussing the last. Oh, first of all, I wanted to apologize because some native English told me that you rather say FAQ, right? Yeah. So that was the FAQ web page of McQuillan, not the FAQ page of McQuillan. Yeah. So I apologize. Okay. So yeah, I didn't know. So. So I was considering this type of equation yesterday, the last 5 minutes. So it's a Wronskian type differential equation for a map from, let's say, the entire plane to Cn. And we saw that the fact that that f satisfies such an equation forces some algebraic degeneracy of the map f, namely the image must be contained in some affine linear subspace of codimension given by the order, expressed in terms of the order of the differential equation. Okay. So one more property of this equation is the following. So suppose you have some phi from C to C, holomorphism. Then, of course, you can look at f precomposed by phi. So what you're doing, geometrically, you're doing nothing, right? You're just reparametrizing your curve. You're going on your curve at different speed, different velocity. And so the image of this curve, of course, has the same geometric properties. It lies in the same affine linear subspace. And you can read this thing also from this equation, because if f satisfies such an equation, if you put this new datum inside, what you get, so if you do something like this, so when you do computation, you observe that when you compute the jth derivative of f composed by phi, then you have to make computations, and you find that there is a first term, which is just f derived j times composed by phi times phi prime power j. And then you have other terms, which depends on derivative of f of lower order. Okay? Okay, so when you plug this thing inside, okay, everything which is of lower order annihilates with the other wedge product of the remaining terms. Okay, and so this becomes just f prime to something, which we're going to compute. And here you have something like this. And of course, this is identically 0. Okay? So what's this number here? It's k times k plus 1 over 2, because you have a jth power for each derivative. So you have 1 here, 2 here, up to k. So you have to sum up the first k numbers, and how, like Gauss explained us, the sum is this, right? So, okay, so so you see, since phi is a holomorphism, phi prime is different from 0, and then you have that one that f satisfies this equation if and only if f composed by phi satisfies this equation. Okay? So you have this sort of invariance by reparameterization. Okay? And that's good when you want to study hyperbolicity of, say, compact manifold, because by what we have seen, this Brody lemma, being hyperbolic for a compact manifold is equivalent to the fact that there is no entire curve. So no entire curve means no holomorphic images of C non-constant, okay? And so you just don't care the way the curve is parameterized, right? You just don't want to have any geometric image of C, okay? So that's a property we would like to keep, some sense. Okay, so with this motivation in mind, I hope it will be a little bit more digest what I'm going to do now. Okay, so now I want to do the same construction, same type of construction, in a totally intrinsic way on manifolds, okay? So the goal is to construct some vector bundle on any given complex manifold whose sections, whose holomorphic global sections can be interpreted as differential equation on curves with the supplementary property that the construction will give us the fact that every time you have one of these global algebraic differential equation, then automatically every given entire curve must satisfy this equation. Okay? So we want, of course, if you take some random holomorphic map here, it's not going to satisfy such an equation, right? But we want to construct a class of equations that are automatically satisfied by all holomorphic entire curve. And so the difficulty will be to say that there is at least one of such equation, right? Because maybe there are not. But you know that if you have one, or maybe you're lucky and you have lots of them, then they automatically give lots of constraints to entire curves. And then maybe you can hope that these constraints force your entire curve to be not Zariski dense or even constant if you're lucky, and then you have hyperbolicity. Okay, so that's the general philosophy. Okay, so let me go inside the constructions. Okay, so you take X, your complex manifold. You have the holomorphic tangent bundle on X. Then, okay, I think I have to make I want to make a little more general construction. So let me also fix a holomorphic vector bundle inside T. Okay, I have a holomorphic subbundle. So I consider the pair XV. So for instance, if V is integrable in the sense of Frobenius, then this gives you a foliation, a smooth holomorphic foliation on X. Okay, but the construction does not require V to be integrable. Okay, it works in general. A special case is when the rank of V is equal to 1, and then it's automatically integrable, and it gives you a holomorphic foliation by curves. Okay. Okay, so now I want to construct this bundle, JKV over X with projection PK. This would be a holomorphic fiber bundle. Of K jets of curves tangent to V. Okay, so what's this? So what is this JKV? So its elements are equivalence classes of maps. I take germs of maps, holomorphic to X. Okay, so this defined in a neighborhood of 0 to X. I also require that F prime belongs to V. Okay, point by point, I want the tangent vector to to belong to this subbundle that I fixed. And I have some equivalence relation. So I fix an integer k, of course. And the equivalence relation is that f is equivalent to g if and only if, as first of all, f of 0 is equal to g of 0. Okay, they go to the same point, right? And f, the jth derivative at 0 is equal to the jth derivative in 0 for f and g for all derivative from 1 to k in some fixed, and hence any, some fixed holomorphic coordinates. Okay, and of course the projection sends an element here to f of 0. Okay, so the base point on the manifolds. Okay, so in some sense you can think this bundle has the kth order Taylor development of curves which are tangent to V. Okay, and two of them are equivalent if the Taylor development differs starting from order k plus 1. Okay, that's k jets of curves. Okay, now now I want to put some right action of some group on this jk of V. Okay, so the group in question will be the following. I take the germs of biomorphism which is, you can think about that as power series in 0, polynomial, I mean degree kth polynomial of this form. Okay, where you just require. Sorry?
So you're going to pass equivalence relation there?
No.
So you don't need the order tk plus 1?
No, I'm putting this here just to recall that composition in this group is taken up to order k plus 1 in the development. Okay, so the group law is composition of biomorphism. Okay, and since these are germs, the only thing I require to be a biomorphism is that the first coefficient a1 to be different from 0, right? First derivative different from 0. Okay, so inside this group, you have the homotheties. Just dilation by some factor. Okay? And so this group act on the right fiber-wise. Just by composition. Okay? You send F to F composed by phi. Okay, this gives an action. Good. So remark? Yeah.
What is that word?
Homotheties. Yeah, I guess. Yeah. Okay. So observe that here, for instance, the case k equal to 1. When you look J1 of V, these are just equivalence classes of tangent vectors, tangent to V, which is V itself. Okay? So for k equal to 1, this is a vector bundle. But as soon as k is greater than or equal to 2, it's no more a vector bundle. It's a fiber bundle, and the transition function are polynomials. Okay? But it's not. It does have no more a linear structure. Okay. So now out of this, I'm going to construct a vector bundle on X, which is called the vector bundles of jet differentials. I'm going to construct two different kinds of invariant and not. Okay, the first construction of not invariant is due to Green and Griffiths, and the second one I'm going to propose you to Jean-Pierre de Mailly, who is likely absent. Yeah, under my suggestion. Okay, so let me construct this bundle as sheaves. Okay, I'll tell you. I construct for you some sheaf, and then I hope you will believe me that this sheaf is indeed locally free, and so it's the sheaf of section of some vector bundle. Okay, so as sheaves, so you fix two integers. So this will be an order, and this will be a degree. Okay, order has an order of a differential equation, okay, and degree as a polynomial, you'll see. So that's the construction. I call this shift like this. Okay, so GG stands for Green and Griffiths, but I'm also going to construct a shift like this without GG, so I put GG in parentheses, okay. So I'm going to describe this section over some small open set. These are the sections. So I want at the end of the day this guy to be some sheaf of differential equation, okay? So you see this bundle jk of v over x, you can think of v to be the tangent bundle, for instance, okay? So on the fiber of this bundle, you have all possible derivatives of maps from C to your manifold, okay? That's the bundle of all possible derivatives of jets, okay? So some relation, some function equal to 0 on this big space will give you some relation among derivatives, right? So in this sense, it will be a differential equation. So let me explain for you. So a section here is a holomorphic function from the pre-image of U. So you take some saturated open set in jk of v, okay, to C, holomorphic. Okay. So for the moment, just K appears. Okay. So at some point, I have to put M inside. Okay. So I want the following invariance. When I compute P on F composed by phi, where phi is some element there which is acting fiber-wise, okay, I want it to be F prime to the M P of F. Maybe composed by phi. Okay, so this is exactly the same kind of invariance that we just look about front scans. Okay, when I compose, when I reparameterize my curve, I want this function to be insensible of this parameterization, except for this scaling factor here given by the first derivative of the parameterization. Okay? So this is for the invariance required for this bundle. Okay? So for every okay. At the end, this is the bundle, yeah, at the end.
How do you put X before? Just
Because I'm describing it as a sheaf.
in this way you said
Yeah.
looking at the sheet.
Yeah, I'm looking at the sheaf. And this notation is misleading, but I just want to say that at the end, this sheaf will be locally free and will be the sheaf of section of this bundle. Okay? Okay, so be calm. So if you want to put here a GG, which is the first construction that has been made in the last 70s by Green and Griffiths, you don't look at all possible parameterization, but only to dilations, to rescaling. Okay? When you look at rescaling, what's going on? Okay? What's going on? So what's going on is that you have this P that you can think of it as some function on the derivative of K, right? So if you compose by some, so phi will be some like lambda times T, some dilation. Okay. So when you compose here and you take derivative, the action is that you are putting here a lambda square up to lambda to the power k. Right? When you derive, you have some factor with some power which goes out. And so what you are requiring here is that this should be equal to this guy here. Okay? So if you restrict your attention just to dilation, what you're asking is that on each fiber, when you think f prime, fk as variables, this function, the restriction to a fiber, will be a weighted homogeneous polynomial, okay, of total degree m, with weights 1, 2, k on variables, okay? But of course, if you let the full group act, it will be some sub-thing of weighted homogeneous polynomial, much more complicated, okay? And we will see at the end of the lecture some example of invariance, okay? Here. Okay, so again, if k is equal to 1, what are we looking for? So in this case, jk of v is just v. Okay, so we are looking to function from the total space to v, of v to c, holomorphic function, which are homogeneous of some degree. Okay, so it's homogeneous polynomial of a fixed degree on this bundle. Okay, so in this case, A1m of v star coincide with E1m GG v star when k is equal to 1 reparameterization adjust dilations. Okay, so it's the same here. And this is going to be the same thing as homogeneous polynomial of degree m on v. Okay? Okay. So as I said, it turns out this sheaf of holomorphic function on this sort of push-forward sheaf turns out to be locally free. And so I call this vector bundle like this. It's the vector bundle associated to this sheaf. Okay? So in case for k equal to 1, you just have this guy here. OK? And another remark. So you can translate quite precisely this observation here in terms of graded bundle. OK? So the remark is that if you take EKM, this GG, that you can think fiber-wise as weighted homogeneous polynomials. Okay? So this is, you cannot think as it globally as weighted homogeneous polynomial. But if you look at it properly, so looking at some filtration, looking at the highest exponential, and then you go down in the filtration. I don't want to be precise. But anyway, there exists a filtration on this bundle whose graded bundle, associated graded bundle, is a direct sum like this, L1 plus 2L2 plus KLK equal to M of FSL1 star. Okay, so you see that by passing to the graded bundle, to this filtration in the graded bundle, you have globally this description as weighted homogeneous polynomial. You see, you have these polynomials, and each homogeneous polynomial, each piece here has a different weight, which participate to the total degree. Okay? Okay, so so you see if you have your X here, you have C here. Suppose you have a map here. And over, let's say, tangent to V, or just take V to be the Tx. Okay, so you don't have to care where the tangency are. Then here take this Jk of V. Okay, so at each point of the image here, you have a well-defined kjet of your map. So you have a map from here to here. Okay, and saying that, and suppose you have some global section of your, suppose you have some global section of this bundle. Okay, so a global section here is nothing more than a globally defined holomorphic function here to C. Okay, with this invariance property. Okay, so you can ask if F is or not a solution for this differential equation, which means that this holomorphic function from here to C will have a zero locus here somewhere. And you can ask if the image of C by this lifting of F sits or not inside this zero locus. Okay, that means exactly to be a solution or not. Okay, so exactly for as in the Wronskian case, in principle there is no reason for an arbitrary F to be in the zero locus of something like this. But here is the magic, and it's always alpha Schwarz. Okay. So there is a fundamental vanishing theorem. So this is due to a lot of people. Let me just credit this theorem. So Green-Griffiths, Siu and Yang, De Mailly, and Noguchi also. And the vanishing theorem is all these people I cited. It's some more and more general vanishing theorem that let me give, and more proof are more and more accurate. And so let me give this final form. So suppose your compact manifold X is projective, and fix some ample line bundle A on X. Or positive if you want. And suppose you have some section of this bundle, even this one, maybe, but once twisted by the dual of A. Okay? So not only I'm asking to have a global section of this bundle, but normally when you twist with something negative, it's more difficult to have a section. So requiring this bundle to have a section is stronger to require that this bundle has a section, okay? But nevertheless, suppose you have one global section of this guy. Then, if F is a map holomorphic from C to X, then if you consider P as a differential equation of order K, and degree n on F, okay, then this is identically 0. Okay? So, meaning that if you have such a section, this means that you no more have a holomorphic map from GK of V to C, okay? But you have a section of the pullback of the bundle A minus 1 up there. Okay, you have such a section. And any lifting of holomorphic map from the plane to X, when you lift it up, it will sit in the 0 locus of such a section. Okay? So by requiring this stronger property of, usually people say vanishing on an ample divisor, then you get this very, very impressive property of the fact that this differential equation are automatically satisfied by all entire curves. Okay? Okay. So of course, this is interesting only if P is not identically 0 and F is not constant, right? But it still holds in this case. Okay. So as I said, this theorem is true essentially by the same argument I gave yesterday, this Alford-Schwarz type argument that tells you that if you have negative curvature, then you're hyperbolic. Okay, it's the same kind of argument. So now I'll try, in time remaining, and I'll try to convince you that this is the case and why. Okay? Okay, so maybe before going there, since I will not able to talk about two of the announced interaction of hyperbolicity and foliation, let me say something about the first case, which I will not talk tomorrow. Okay, so out of this kind of bundle, you can construct a locus on X, okay, which is called the Green-Griffiths locus. Okay? So I don't want to be very precise because the definition is a little bit, yeah, it requires some time, but you can imagine it like this. You fix some ample bundle, okay? And you consider all possible order k and all possible degree m, okay? And you consider all possible section of this bundle when it's twisted by a minus 1, okay? So this gives some base locus on jk, and on all of this jk going up and down, okay? And by the theorem, every holomorphic map, when you lift it up, must sit in this base locus, okay? And now you intersect all these base loci, so maps will have to sit in this intersection, and you project down onto x, okay? So this is a projection. X, projecting to x of all base loci of a, k, m star tensor a minus 1 at the different floor of jk of b. Okay? And since your map is a lifting, okay, thank you. So since your map are liftings, which means that the diagram commutes there, the image of f, of an entire f, like this, must sit in this Green-Griffiths locus. Okay? So in other words, you have this exceptional locus of x, which is the union of all image of C, of f entire, and you take the Zariski closure. Okay. And this fundamental theorem tells you that you always have okay, that's what I'm saying. Okay, so you always have inclusion. So at some point, at the beginning of the theory, so Long was asking if maybe this locus is enough to characterize this other locus here. Okay. Do you have equality? Okay. So of course, saying that x is hyperbolic, it's the same as saying that this exceptional locus is empty. You have no entire curve, okay? And if you want to solve, for instance, why not, a Green-Griffiths conjecture. So if you want to show that a manifold general type has a manifold containing all images of entire curve, okay, so you must show that this guy here is a proper subvariety, right? And maybe you can show that this guy is a proper subvariety, and you're done. Okay? And if you have equality, you also have this impressive property that you can describe this analytic locus in terms of zero of section of some bundle. Okay? And so the answer is no. So you have two questions. Are these two loci equal? Question 1. And question 2, is it true that if the manifold is of general type, then this locus is not the entire manifold? Okay? And the answer is no. No. Okay? So just very quickly, I can cite. So I have this. We constructed some example with Erwan Rousseau and myself. And so the examples are, you take X to be a compact free quotient of a symmetric bounded domain. Then you have a dichotomy, either or either. I don't know how to say. Either. You don't have any opinion? You're English, right? No opinion. Okay. Either. So either omega is the ball, and then you have that Green-Griffiths locus is empty. So indeed, in this case, the cotangent bundle of X is ample. And since it's ample, the cotangent bundle, and since the one jets are precisely the section of the cotangent bundle of symmetric powers, you don't have any base locus even at the first step. Okay? So this is, or you take any other bounded domain, symmetric bounded domain, and in this case, you have that the exceptional locus is empty because X is hyperbolic. And you have strict inclusion with the Green-Griffiths locus, which on the other hand is it's everything. So you have the worst possible situation here. And indeed, you don't even, so I wanted to speak about this thing because to show this property, you use foliations, okay? But I don't have time, I'm sorry. So, but there is also even a simpler example where you have this property here, is when X is a product, non-trivial product of two manifolds. Okay, so you take two hyperbolic compact Riemann surfaces, genus 2. You take the product, it's hyperbolic, and the Green-Griffiths locus is everything. Okay, so even in this simple case, if you didn't know that it was hyperbolic, you couldn't use just the jet differential to prove hyperbolicity. So in general, when you want to prove algebraic degeneracy or entire curve or hyperbolicity, so what has been done up to now is more or less to couple jet differentials and foliations. Okay, and hopefully this is what we're going to see tomorrow. Okay, in the lecture of tomorrow. Okay, so I have 17 minutes. Okay, so let me try to convince you that you have this vanishing theorem, okay? So to do this, I will construct for you this Dunaï sample jet bundle tower, okay? So it's a construction of some vibration over X. And at each floor of this construction, you have a tautological line bundle, like in the projectivization of a vector bundle. Indeed, it's a successive projectivization of vector bundles. And this tautological line bundle up there on this more complicated manifold of higher dimension has the nice property that if you push it forward as a sheaf on X, then you recover exactly this vector bundle of jet differential. Okay? So exactly as you recover the section of symmetric power of a vector bundle by looking at the O of 1 on the projective eyes, then you iterate it and you construct bundle of this, the section of this guy there. Okay, so let me do that. So here's the idea. It's an iterative procedure. You start with your xv, and you construct some x1 v1, and then x2 v2, and it's done. So how you construct this? So your x1 will be the projectivized of lines of v. So I don't put the double bar here because it's a projectivization of lines of v, not hyperplanes. Okay. So you have this x1 here over x. So the dimension here of x1 is n, the dimension of x, plus r minus 1, where r is the rank of v. Okay? And now, here, you have the tangent. You have the tangent bundle over here. And you want to extract some subbundle, as you did for v in Tx. Okay, so how do you do? So you look at the differential here. So the differential map from x1 to, let me call this pi 1. So pi 1 star of Tx. Okay, so the kernel here is exactly the relative tangent bundle. Okay. But now, I mean, inside Tx, you have v. Okay. So I would like to replace something with something smaller. Okay. I start putting v. Okay. Then you don't have any more of these. Just give me 1 second. Okay. And when you projectivize your v, how do you construct your O of 1? What you do is that you take the pullback of v, okay, and tautologically, you select on each point of the projectivization, you select in v the line which correspond to the point that you are projectivizing. Okay, that's the tautological construction. Okay, so here inside you also have O of minus 1. Good? And then you put here what you need to be this thing exact. You put a pre-image here. This is V1. So what's V1? It's a subbundle of the tangent bundle of x1, which selects which directions. So all the vertical direction plus just one horizontal direction. Okay? And which is the horizontal direction you select? It's exactly the direction given by the point on where you are sitting on this projectivization. Okay? Yeah, it's a little bit messy, I'm sorry. But anyway, this has again rank R. Okay? This was rank R. The relative dimension is R minus 1. So this is rank R minus 1. This is rank 1. So this is rank R. Okay? Good. So you have a tautological line bundle here. You have some V1. Good. So you have X1, V1. You start again. Okay, so at each step, the dimension of x increases. So this is n plus k time r minus 1. And the rank of v, it's always the same. It's always r. And in xk, you have this tautological line bundle. Which is for free because xk is obtained by projectivizing some vector bundle at the preceding step. So you have a tautological line bundle on xk. Okay? And this is the one. Okay? So you have this theorem. And so you take pi k, which is the projection from xk to x. And then you take the direct image of the sheaf oxk of m, an integer. So this is a sheaf on x, and this is the sheaf of section of akm v star. Okay. Good. And now, suppose you have a map from some neighborhood of 0 in C into xv, meaning that the tangent direction are in v. Okay. Suppose you have a map like this. So over here you have x1, v1, and they claim that you have a lifting here, which I call f1. So how is the lifting obtained? So a point in x1, you can consider it as a pair, a point on x, and a direction, right? And the direction in v over the point x, so minus 0. Okay? And so the lifting here is just the pair f direction of f prime. Okay? So maybe someone of you might notice that if f prime is equal to 0, then it's not well defined. Okay, but it's not important. No, I mean, if f prime is t to the power k times some non-vanishing holomorphic function, then outside 0, the class, the projective class of t to the power k times u and u are the same, right? And then you define the projectivization just as the class of u. This remaining, you divide by the higher order of vanishing of f prime at that point. But anyway, it's well defined. And you see also that if you compose f, you reparameterize f, and you lift it up, this is just f composed by phi. And here you have the class of the derivative of this guy. But what's the class? It's f prime times f prime composed by phi. Right? But this is different from 0. So that's the same as the lifting of f composed by phi. So this lifting of curves are intrinsically invariant. Okay? And what you can check also is that if f was tangent to v, when you lift it up, the new curve here will be, it's tautological indeed, tangent to v1. Why it is? It's because f1, if you compose by pi, you get back f, right? You project here. You take the differential of this. And you have this guy here. And this means exactly that, but f prime gives you the direction, gives you the point where you are, right? So tautologically, the tangent direction projects onto the only horizontal direction that you have chosen, which corresponds to the point where you are. And that's the definition of v1. Okay, so you are in v1, and so you can start again. You can lift it up. Okay? And so you get some well-defined kth lifting from C to xk vk. Okay? Now, 5 minutes, fair enough. Now, as you can imagine, I will be a little bit sketchy, okay? But nevertheless. So, suppose you have some section, P, of this bundle. Okay? Good. So, by that theorem, this is the same thing. This corresponds, this is isomorphic, to a section over xk of O xk of M tensor pk star of A minus 1. That's by the projection formula. Okay? So the fundamental vanishing theorem I would like to prove now becomes that the image of fk there in xk is sitting in the base locus of the section of this line bundle. Okay? But the fact that this bundle twisted by something which is anti-ample, I'm cheating a little bit here, okay? A is ample on x, no more on xk, but still. You're twisting with something which is anti-ample, okay? So by the Quadratus lemma we saw last day, okay? This guy is big. It's a big line bundle, okay? So this in okay? And you can construct on it a metric, a singular metric with positive curvature, whose degeneracy set is exactly along the zeros of the section. Right? That's what I said. Okay. Let's say that this corresponds to a section sigma. Okay? So it has a metric, singular metric, positively curved, and with the degeneracy set sigma minus 1 of 0. Okay? So I don't want to steal you any minute, but let me conclude the argument just at least from a heuristic point of view. Okay? So you have this xk, and here inside you have this z, which is sigma minus 1 of 0. Okay? Now you have this map f, k, which goes here inside. Okay? So what you do, you want to show that the image is inside z. Okay? So if not, it will cut z, but it's not contained in z, right? So except from some countable number of points, okay, you can pull back this metric, okay, and you can apply something like Alford-Schwarz lemma. It's the same kind of reasoning, okay? You make the same thing by pulling back this metric from there, which is positively curved, but it's living on some dual. So when you pull back indeed, and you see on the tangent space of C, you get something which is negatively curved, okay? I'm sorry if I'm going very quick. But But anyway, positively means negatively indeed. Okay? And so you can really pull back something which is negatively curved on C. And so, as I did, you see this on bigger and bigger disk, and you can compare with the Poincare metric because of the negatively property of the curvature. And so if you're not sitting inside Z, where everything is degenerate, you can apply the same type of argument as in Alford-Schwarz lemma, and you get a contradiction. Okay? So you need to sit in Z, because in that case, the metric is just plus infinity everything, everywhere, and so there is no thing that you can prove with that, okay? And that's why you have to sit inside Z. Okay, I'm done.